Hello, this is David Birch at Star Path School of Navigation in Seattle with a video note on how to plot a celestial fix, 2 lines of position, using an Echart program, electronic charting system, and I'll use OpenCPN. That's a popular one. And so here's show our textbook, because I'm going to do an example from the textbook, Celestial Navigation textbook. And that is here. These are some plotting exercises. When you do take a sextant site and finish up the paperwork, you end up with this type of information. It's then just a plotting exercise. You have this altitude intercept here equals 20 minutes toward that direction, 340, starting from this position. And so you have, this is one site, this is another site, and you plot them and you get a fix. And so when you do this on a universal plotting sheet, it is some exercise like this over here. What is this? 1 and 2. This is number 1. That's at 35 north, and then 145, 18 west. So 145, and you go over to 18 west, and you make a mark, and then you draw a line in direction 340. Zn equals 340, that's that direction, and you move toward it. A equals t, that's toward 20 minutes in that direction. Then you construct a perpendicular. That's how you plot a line of position, using universal plotting sheets and parallel rulers and dividers and regular tools. Then you plot the other one, let's say 1 star, 2 star, and where they intersect, that's your fix. So that's the exercise, and we have some, just isolating that part of the process in our book, we have these exercises, and some question came up about the answer to this one, and so I'm going to work this one as the answer right here, number 9 and number 10. And so let me just go down here. Okay, and so here's the problem. Okay, there's the 9 and 10 data right here that we're going to do. And I had okay, so the way you would do this, and I have it already done, so it's not going to take me too long. So the first thing you want to do is you got to plot the assumed position. And the way that you would plot the assumed position in a charting program like OpenCPN is just go along here anywhere, right-click, drop a mark, go here and say Properties, and then give it a name, APLOP4, whatever. And then this, in standard celestial navigation, using tables, this is latitude's always going to be on a whole number, so that's 35. And let's say this was 45. Let's say that my assumed longitude was 145, 53.6. And I just put that in there and say OK. So that's plotted, very accurately plotted the assumed position. Okay, so let's just do number, what's this? Let me zoom in here. The number 10, LOP. I'll just do number 10 as an example. Number 10, right, this one here. So I've plotted that in the right spot, show in exactly that method. Then I want to draw a line, number 10, in direction, oh look, I'm going away. I'm going 34 minutes away from the direction 92. So what you have to do then is take 90, since it's easier to draw a vector towards, you just say 92 plus 180, that's going to be 272. So then what you would do is go to a route tool, like this route tool, and then you would just say drop a line here, and then you see it's reading out, that's 287, and then you just keep going like that. That's the way you can draw a line. Escape, I want to get rid of that, delete. Okay, delete. Yes. Now, but I forgot something. The way to make this a little more accurate, we know where we're going to draw. Basically, remember the original picture. You draw the assumed position, then you draw a line in the direction of the azimuth line. This is 173, either towards or away, or no. Oh, I'm doing number 10, 92. You're either going towards 92 or away from 92. I'm going away from 92. So I'm going to draw a line in direction 272, like that. But then I'm going to then construct a perpendicular to 272 at this distance 34 minutes. So the most accurate way, because there's always, even though we can zoom in and do this very carefully, all these, it's a lot more accurate just to go in here, take this assume position, right click it, go to the properties, and put a range ring on it. So I said show range rings, put one ring on it, make that ring 34 nautical miles, 34.00 nautical miles, okay? And that's this blue line right here. So then all I have to do, I don't have to worry about making that line exactly right. I just draw this out here, this line in direction. See, that's 272. Now, here's the other thing. You see, this one's also 272. So what I did here to illustrate this process is because you can only read this to the whole degree on this charting on OpenCPN. You read the bearing line when you do something like, I'm hitting the M key, right? If I hit the M key and then come out here, you see that's 285. That's 285, and that's 39.8 miles long, and so forth. But you see, that's 282. Look at, you see the number there, 282. Now look, I'm coming. That's 282, okay, and there's 283, 282. It just turned 282. Now I come down. Look, I'm still going down, 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 down. That's a whole degree. Whoop, bang, up. So right here is where that's turning to 282. And that's like that, an escape. And then so what these two lines here are marking is the width of 1 degree. Basically the width of 1 degree when you don't have tents. So the first line, the first azimuth line is coming out. We want to draw it in precisely I think it was 272.0. So I have to kind of mark it that way. Now this is, again, I'm trying to get this really accurate. That's why I'm doing it this way. You could just draw it out and drop it and you're okay. And then I'm going to start this line from, it's not exactly right. You see, if I zoom this in, this line really should be, let me go right here, properties. Now that guy really should be over here just a little. He should be right there, right? Now, okay, that's okay. Now I've got to come up here. I'm rolling this with my thumb. I don't know why. My first finger, I'm rolling the mouse roller. Okay, so now there's this one. Now, can I move that? No. The only way I can move that in OpenCPN is show the properties. At least that's the way I have it set up. So I can show the properties. And so, but look, once you've done it, here's the other trick with using this. Once you've drawn the line, you don't get a dynamic feedback. You can drop it and then come back and read it and drop it and read it and so forth, right? But that's not very tidy. So basically, you have to really start over again, to get it dynamic. So in other words, here's my first line. That's the azimuth line coming out here. Then I measured out to 34.0. Was that 34.0? Yeah, 34.0 away. And then I draw the line. Then I'm just going in here and drawing another vector, basically one-legged route, right? So I go here. But now it'll be dynamic. So I click here. That'll grab that point. But now you see it's dynamic and I can read the bearing. What I want here is 90 degrees off of that one. So this one's going to be 02. So you see there's 02 coming this way. 1, 1, 1, 2. So that's 2 right there. That's 2 right there. Bang. Okay, escape. Now I'm going to get rid of this one because I moved that point. Delete. Yes. Now I'm going to come down and do it again. Again, I'm trying to squeeze in accuracy of half a degree here. Now here I'm going over. Let me start out here. See, there's 9, 8, 7, 6, 5, 4, 3, 3, 3, 3, 3. Oh, it's pretty close. That's interesting. Oh, okay. But, so that's the way it works. So this one then, I put the second assumed position in. I put the range ring on it, which was going to be at 29 miles. And then it is in direction away from 173. So that is, 173 plus 180. That's 353, and then I draw the line. Now, the intersection of these is then a plot. Now, I've talked about this, and it's taken a long time, but this really just takes a couple minutes when you're doing this. You don't even have to horse around like with this kind of 1 degree bearing stuff. You don't even have to do that. But you see, there's the fix. That's a fixed position right there. And that little green dot is the answer that's in the book. So that all looks okay. Again, that's within the 1 degree. 1 degree. Let me show something here. Here is a browser. Here's a browser, and what's going on here? This is this line. Let's do this one here. This we know is about 30. One's 29 miles. One's 34 miles. Let's just look at how big, what's this distance here? One degree after 34 miles. And that's a tangent. So you can just say equals you can go to a browser, say equals a tangent 1 degree, enter, like that. That's a tangent of 1 degree. And then multiply that times 34 equals. So you see, that's about 0.6 miles. So this distance here between these two, let me zoom way in here. This distance from here to here, that's 1 degree, about 34 miles away. Now I'm hitting the M key, and you see, what do we get here? Well, that's 0.48, 0.5, something like that. I didn't use, well, this is 29, not 34, etc. So you see, that's about the 0.5 miles. So when you want to be really careful about this plotting, then you have to take this stuff into account. But anyway, there's a way that you can plot a celestial line of position very accurately. I should probably do one just bang, bang real quick without all the discussion to show how fast it is. And that's a way to get it's faster than plotting on a sheet of paper generally, and can be more accurate.